Chapter 5, what we're going to cover in Chapter 5.
What are we
Normal distributions. We're going to talk about normal distributions. We've talked about some of them throughout the year a little bit. The normal distribution that we're going to deal with the most, that's the normal distribution. All we've been calling it the bell curve. We're going to use that to find probabilities of finding values in the normal distributions. Make sure you got those charts. We're going to need those charts. I think the very front page of the chart says normal distributions, the front page and the second page. Right, it says standard normal, I'm sorry, I'll mess that up because there's a difference between normal distributions and standard normal distributions. Be able to approximate the stuff that we were doing last chapter, and we're going to talk about that. Be able to approximate those into normal distributions. Not everything, even when we have a bell curve, when we're talking about a bell curve, not everything in the world fits a bell curve, but a lot of the stuff we're going to approximate to fit that. So first section here, interpret graphs of a normal probability distribution, find areas under those. So we're going to find an area like we might be looking at this area. Maybe Braden on his ACT scores right here, and he wants to know how many people in the country are not as smart as him that took the ACT test or something. So we'll find that area underneath there. Last chapter we talked about discrete probabilities. We also talked about continuous at the very beginning of the chapter. This chapter we're going to talk about the continuous. Remember, discrete was if we were on a number line and you were looking at the number line. It just had the points here, here, here. It didn't include all the stuff in between. Continuous includes all of that. So that's what's going to be different about this chapter. Instead of just looking at 3, 6, 9, 12, 15, 18, now we're looking at everything from 0 to 24, including stuff that falls in here. So there's an infinite number of possibilities. And it's represented by the interval on the number line instead of just those certain points. And that's the main idea of this whole chapter, is dealing with those continuous random variables. Said he quit baseball, my oldest son. And it's probably the same thing with Travis. My oldest son in fifth or sixth grade, somewhere around, how old would you be, 10, 11, 12. He got to about Little League, and he quit. And then a couple years into it, after he quit, he went back, but they didn't tell me they went back to play. And the reason he quit was, I guess, because of me. So now when I sit out in the outfield, that's why I sit way far away from everybody, because
So you're not telling them what you're doing.
not yelling at them. And
That's how I'm gonna be, I feel like, for something. What are you doing, dude?
Yelling at him,
Yeah.
he can't hear you.
when he came back, I mean, he quit for a couple of years, and then he came back and he was playing like 15, 16, 17-year-old ball.
He did everything pretty good.
He was fairly good. I thought, dang, I should have kept my mouth shut, I guess.
There was a guy that got inducted. I didn't know. I never even heard of him. He had a bit better ERA and all that than Travis Park.
Really?
Kevin Havlin guy. He was
Oh,
on
yeah,
at
Havlin.
school the other night. He had a better ERA than all them.
Nobody, and I don't know, I could be wrong, but it seems like with Havlin, if you talk to some of the other people around, I don't know how close your dad was with him, but some of the other people his age,
He said he kind of knew it, but
yeah, see, that's what I sort of knew him, but most of the people his age didn't think a whole lot of him and thought that, I think it was Dimmer. Maybe Dimmer was sort of a little partial to
Loved
him.
him. Mr. Dipper was at the school too. It's the first time I've seen him in forever.
Yeah, he kind of looked good too.
Still looks the exact same.
Little older. Little older, but still.
Yeah, I think I seen him driving down the road eating the other day, I thought, or walking down the road or something. So continuous probability, and this is just saying the same thing, is just the probability of distribution. We're going to talk about that. What this is going to do, last chapter and up till now, we've dealt with stuff like this. Now we're going to change it into this curve. We're not really changing it into that curve. It's that curve anyway. But part of what we're going to do later on in this chapter is you're going to look at the stuff that we've been doing, and it's going to sort of estimate it to fit that normal curve. So you can see here, and when we estimate this, and we'll talk about this later on in the chapter, you can see some of this like gets left out, but probably about like when you were back in first grade or second grade and they gave you those little blocks and it had something like this, and it said, estimate the area of the triangle. And some of you were smart, and you know, some people weren't so smart, and they go 1, 2, 3, 4, 5, about 5. And then others of you go, oh, well, you could take this little piece and stick it right here, and take this little piece and stick it right here, and make another whole block, and then you count it all up and sort of estimate it. That's what this is going to do. It's going to take this and say, well, that about fits there. This part might about fit there. This part might about fit there, and just estimate that whole curve. All right, so we're going to take what we had as a histogram and sort of change it into that normal curve. A normal distribution is a continuous probability distribution for a random variable x. That's what we've been dealing with the last couple of chapters, is just our random variable x. It's the most important, or the one that is the most important is the normal curve. That's what we're going to deal with. Everything is going to be based off of that normal curve. We've been calling it the bell curve. Doesn't matter, I don't care which one you call it. There's probably some mathematical thing that says you should not call it the bell curve. It should be called the normal curve. It doesn't matter to me.
What you think about the Bengals finally winning the playoff game?
I don't think much of Burrow.
You don't like Joe Burrow?
I like him all right. I just don't think he's everything that everybody's making him out to be. It kills me that who were they? Who was it? One of the other teams that lost. They were just hammering their quarterback. And he had, well, I think it might have been the Cowboys.
Oh, Dak Prescott.
Prescott had 250 yards, 250 some yards, and a touchdown and an interception. And they talked about how terrible he played.
He just did a dumb play the last play of the game.
Right. And, you know, but they they said it on ESPN, they were just talking about how terrible we played. And then you look at Burrow's numbers, and he had 244 yards and a touchdown or something like that. And I'm thinking, these numbers aren't that much different.
I didn't think Joe Burrow played very good.
I didn't think he,
I think the comparisons to Tom Brady and all that are a bit
that's
early. He's got a lot to do for he's Tom Brady.
That's totally ridiculous. And they out there at the end of the year, they talk, oh, how great he is, how great he is. 2 weeks before those last two games, they were talking about how terrible he looked.
He looked horrible.
Oh, but he's fifth in yards, and he's this, and he's that.
He's also first in interceptions.
Yeah, first in interceptions, and they, well, his offensive line's horrible, that's why he gets sacked so much. And I'm like, no, sometimes he gets sacked just because he's afraid to get rid of the ball. A lot of times he's stood in there too long, or he doesn't read the defense right. When you see that they got 7 guys on the line of scrimmage, you ain't got time to take a 5-step drop and
You hike it and you go.
I hate Roethlisberger, but boy, he gets rid of the ball. He didn't want to get hit anymore. This year he was done. He just, all right, you hike me the ball, I'll throw it.
He might only throw it 5-6 yards too.
That was great.
Yeah, my dad's like, last time the Bengals won a playoff game, I was 6 years out of high school.
Yeah, it's been a while. So a normal distribution again, that's the bell curve. That's what we're going to do a lot of. We're going to talk about what a standard normal distribution is here in a second also. That's part of it. Lily didn't get it. Properties of a normal distribution. Different properties. First property, the mean, the median, and the mode, all the same, and they're all right there. So on a normal distribution, the mean, median, and mode, they're all equal. They're all that one thing right in the middle of the bell curve. It's bell-shaped, and it's got to be symmetric. So in other words, the left side is exactly the same as the right side. And again, when we talk about the bell curve, there's nothing in life that works out perfect. Nothing's going to fit this exactly. But some stuff are going to be really, really close to being normal. And we're going to use if it was exactly normal to fit everything. The total area under the curve's always equal to 1. So it's 1 whole, or next section we'll talk about it as a percentage, 100%. And the normal curve, and in other math classes you've dealt with stuff like this, it keeps getting closer and closer to the x-axis here, but it never actually touches it. So it never closes. It never touches the x-axis. It keeps getting closer and closer and closer and closer. Other classes, you probably called that a limit. So when you had your graphs and it got closer and closer to that, but it never actually got to it. I like Burrow and everything, but like that game against the Raiders, his first 5 passes were to Chase. You can't.
That's why I think Boyd's gonna leave. I think Boyd's gonna leave.
Probably be 2 or 3 of them.
I think, well, Higgins had a couple big games, but Boyd only gets like 20 yards a game.
Yeah.
And he's good enough to be a number 1 on some teams.
Yeah.
And I'm scared. I think we can beat the Titans. I don't think we can beat the Bills or Chiefs. I don't think we can beat the Chiefs again. And the Bills are playing out of this world right
Yeah.
now.
Hopefully the Bills beat the Chiefs, and boy, I was sure hoping that New England would beat the Bills, and then I was gonna root for Pittsburgh for
I was
the only
hoping
time
Pittsburgh
in my life, and that way we could skip all those.
We wouldn't have to play the Bills or Chiefs. The Bills scored every drive. They didn't punt once.
Hopefully they get all that out of their system against the Chiefs, and then if we do have to play them, that they'll, Josh Allen will be back to what he normally is, where he's sort of erratic.
Yeah. I just love the Cowboys lost. Because Rod and Trav and all them were big Cowboys fans, and they were all mad.
So just looking at this, and we're gonna talk about this also, the mean's gotta be right in the middle. So the area underneath this is always one whole. So that means the area on this side is gonna be 0.5, the area on this side is gonna be 0.5. Or if we're dealing with percentages, it'd be 50% on one side, 50% on the other. We're not gonna, with this, we're gonna draw something else later on that's gonna be more like this. And we drew this earlier this year. Just remember, on our normal curve, you got your mean right in the middle, your 1 standard deviation below, 2 standard deviations below, 3 standard deviations below, 1 standard deviation above, 2 above, 3 above. And that's usually how far out we go, because everything else, if anything's outside of that, it's very, very unusual. So that's all this says. These points, we're not going to get into this a whole lot. They're called inflection points, and it's where the curve changes. The curve, as you're going to here, is going one direction, and then when it gets to that point, it switches, and that's what this explains. So between here and here, the graph curves downwards, so we're going downwards here. But then when we get to here, and I know it's sort of hard to understand, it starts going up. So, and those are called inflection points. We're not going to do a whole lot with inflection points. But the standard deviations and stuff, we are going to do a bunch with it. We'll have to draw these graphs, and you'll have to draw them. We did that earlier this year. So not a whole lot of this really makes a whole lot of difference. The inflection points, again, don't worry about this slide. At 1 standard deviation below and 1 standard deviation above, that's your inflection points. And that's where this center part of the graph is. That's sort of important. We will talk about that, but just think about the standard deviations. Probability density function. We've been doing all this stuff on the calculator, and it said PDF and CDF. PDF stands for probability density function. That's what that stood for. That's all this is telling you. This is the formula to draw the normal curve on, if we want to graph it out, that's the formula to graph it out. So Braden's bored and he wants to go home and graph all these normal curves on a piece of graph paper, he can use that formula. Now, as you write this down, you're probably going to be mad at me here in a minute. We are not going to graph these. Not this way. Alright, we're not gonna sit here and punch all that stuff into our calculator and get out a little piece of graph paper and graph it out point by point and do all that. When we draw our normal curves, it's gonna look like this. I'm gonna draw that, I'm gonna draw that. I'm gonna draw this, I'm gonna draw that. And that's all I'm gonna expect out of you, is that you know how to sort of draw it. We're not gonna draw it perfect using the formula. Now, if you look at this formula, the only thing that changes each time is your sigma. What's sigma stand for again? Standard deviation. And your mu, what's mu stand for again? The mean of the population. Everything else in there, pi and e, they stay the same. Those are the things that are going to change throughout the problem. But again, as much as I know Lily'd love to, we're not going to graph this on a piece of graph paper or anything. We're not going to sit and do it. Now, should every normal curve look like the ones that I draw? No, some of them, and that's where this changes. Mine looks like this, and I'll draw the same thing just about every time. This right here would be considered a normal curve also. So normal curves change, all right? As long as they fit all the criteria that we just wrote down on the other stuff. Mean, median, and mode are all the same. They're symmetric. The area is always one hole underneath. So they don't always have to look like this, but when I draw it, 99% of the time, that's what it's going to look like. And I expected probably that's what it's going to look like when you draw it most of the time also. This all says the same thing. The pi and the e stay the same. Symmetric. I'm going to skip over that. Means and standard deviation. Normal distribution can have any mean, any positive standard deviation. The mean gives the location of the line of symmetry. Standard deviation tells you about the spread. Something like that. I'll give you a second on this. This is sort of important. Don't worry about the inflection points, but you see how they look a little different. I'll talk about that here in a minute. Why the normal curves look different. I believe the next few slides talk about this also. If you look here, we can find the mean. The mean of this first one looks like it's about 3.5, 3.5. The mean of this one looks like it's also about 3.5. So those two have the same means, but what changes on these two is they must have different standard deviations, different sigmas. And what the sigma does is it either spreads out the graph or shrinks it up. So the sigma here must be bigger than the sigma here. So this one has a smaller standard deviation, that's why it's more compressed. Then you notice with these two, they look the same, so they're spread out the same, so that means that their sigmas, their standard deviations are the same, but their means are different. This one looks like it's got a mean about 1.5, that one's got a mean about 3.5. So that's what makes things different here. The mean tells you where it's going to be located on the graph. The standard deviation tells you how it's spread on the graph. Just a couple examples here. Which normal curve has the greater mean? A or B? Which one has the larger mean? A. The mean would be right here somewhere, so it'd be A. Which curve has the greater standard deviation?
B.
B, because it's spread out more, right? So it's going to have the bigger standard deviation means you're spread out more. Which curve has the highest mean? C. Which one has the largest standard deviation?
B.
And if we were going to find the line of symmetry for each one, where's the line of symmetry for A at?
A little bit past
For B,
like 13.
and for C.
Middle.
And you should be able to estimate those. We're not going to estimate them right now. It's 12.2 or something, whatever, 13.1, somewhere close to that. Scale test scores for the New York State Grade 8 mathematics test are normally distributed. Everything that we do has to be normally distributed. The normal curve shown below represents this distribution. What is the mean test score? So they just want you to estimate. What's the mean test score? 6 what? 6, 7, I don't know what, 5?
Yeah, 675.
All right, we'll go with that. Estimate the standard deviation. So if the mean's right in here somewhere, standard deviation, remember that's going to split this up into like 3 parts here evenly on each side. About how much do you think it is? Well, if you said this was 675, what's this next one look like? It goes up about 2.
700.
So about how much? 25, 30 maybe if my lines were a little straighter, somewhere around there. It's probably pretty close. 675, that was good. And they said the standard deviation was about 35, so my lines weren't drawn very well. That one was drawn pretty good, that one was terrible. Of course, the one we went by was the terrible one. To graph the normal curve, don't write this down. We're not going to graph the normal curve on your calculator. Trinity wants to see the normal curve graphed on her calculator, that's fine. She could write this down. I don't like doing this. When Mr. A was here, he could do all this stuff and explain to you on the calculator what to do. This messes up your windows on your calculator. You guys ever have to deal with the windows and stuff and change the windows and everything?
And pre-calc.
And pre-calc, and it's a pain in the butt, right?
I just didn't do it.
Because every time you go in there and you change the window, then when you go back the next time, it stays changed and you gotta go back in and change it again. So we're not gonna do this. We're not gonna graph them, but you could graph them on your calculator and do all that stuff. Standard normal distribution. so this is standard normal instead of just normal. This is what changes from the normal distribution to standard normal distribution. It makes all the normal curves look the same, uses the mean as 0, the mean is always 0, uses each standard deviation, so each sigma is 1. The z-scores are on the horizontal axis. All the x's, which are your raw scores, all the x's, if we need to, we could change them into z-scores. We did this earlier this year, and we're going to do a few of them here in a second, just by using that formula. Main thing, remember, x is your raw scores, z is your standard. So you change everything so that you can compare anything together if you change them all to standard scores. We're going to change a lot of our raw scores into standard scores, and that's the only way that chart that you have, that's the only way that you can use that chart, is if everything is changed into standard scores. Then also we're going to learn how to use the calculators and sometimes leave them as raw scores to figure out what we need to figure out, whether it's a area, probability, whatever. So all the standard normal distribution is you taking all the raw scores and changing them into some standard z-score. So you're taking all the, whatever the scores are, whether it's a weight of a person or whatever it is that we're dealing with, and you're changing them all into z-scores. So maybe Ebersole's doctor, when I go into my doctor all the time and they weigh me, they put my weights on some table, and so that everybody's not making fun of Ebersole for being fat, they change them all into z-scores instead of giving the raw score. When we change those scores, again, we did this earlier this year, you take the value minus the mean divided by the standard deviation. So whatever the value is, whatever Ebersole's weight is, goes in here, minus the mean, then divided by the standard deviation, and that gives you a standard score. So that you can compare my weight to anybody else's weight, or whatever it is that we're comparing. An example here, you scored 25 on the ACT, 1130 on the SAT. Which score should you send with your college applications? Do what? The 25, is that the one?
Yes, it's better than I did on the ACT.
So because it's better than you, that's one you should send?
Yeah.
We want to know which one of these, if you're sending one of these scores so that you can look good for this school that you're applying to, which one should we send? Well, we can't really compare those two the way they are. You can't compare 25 to 1130 because they're two completely different kinds of scores. But if we change them both into a z-score, then we can compare them. So first, the ACT. We take 25, that's our value. We subtract off the mean. The mean ACT score of all students who took the ACT last year is 20.8. And we divide it by the standard deviation, which last year was 5. Somebody help me out and figure out what that is on your calculator. 25 minus 20.8, and then divide that answer by 5. And if you tell me 21 point something or 20 point something, I'm gonna be mad at you.
Yeah, but I don't know if it's wrong.
Is it 20 point something?
No,
That's probably correct.
it's 28.4.
Anybody else get that?
Nobody else did it, Mr. Rivers. So it is. Okay.
Now, if we do the SAT one, same idea. We get 1130 minus 1060 divided by 217. So which one should we send? The ACT score. Now again, what this is saying, so make sure you just guess like that on the next test.
Okay.
Right? What we're saying is if we change all these into z-scores, zeros right there in the middle, 1, 2, 3 this way, -1, -2, -3 this way, our ACT score falls about right here. Our SAT score falls about right here. So the ACT score is actually going to look a little better on your application than the ACT score, than the SAT. Did I say that right? The ACT is going to look better than the SAT. Now, also don't forget, if we were going to draw just the standard curve for the ACT. We did this earlier this year. What number goes right there in the middle for the ACT?
20.8.
20.8. Then what do we do to find each number out past that?
You go up 5.
So 25.8, 30.8, 35.8. Then going down, we just subtract off 5. Hopefully Lily was complaining about her score. Hopefully it's not down here somewhere because
Hey.
that is very unusual.
No, it wasn't that bad.
Okay, so
Pretty bad.
you're not very unusual then.
Just a little bit.
And remember, anything, and we'll talk about this, there's a certain percentage that falls in here, a certain percentage that falls in here. Anything that falls past 2 standard deviations away is unusual. Anything that falls past 3 standard deviations away is very unusual. So again, standard normal distribution with a mean of 0. The curve's always going to look like this. This is the standard normal. It's always going to look that way. We talked about that earlier this year. It's always going to, 0 is the mean. It's right in the middle. Then you go 1, 2, 3 on the right, -1, -2, -3 on the left. So that's standard normal. If we were just doing the normal distribution, you would have your raw scores here instead of your z-scores. So it might be the 20.8, and then going up by 5 or down by 5 each time. If each data value of normally distributed random variable x is transformed into a z-score, the result will be that normal curve there. That's all this is saying. So we're changing from normal to standard normal. The formula for a standard normal. So again, if we were going to graph this on a piece of graph paper, for the normal distribution, it's that. For standard normal, it's that formula, which, even though it's not easy, it's a whole lot easier than that one. Again, as you get mad at me here, how often are we going to graph these this way? Never. So we're never going to use those formulas to do the graphs. When I ask you to do a graph, you're going to do this. And draw some little thing like that and estimate. And 0 here, 1 there, 2 there, 3 there, -1, -2, -3, and so on. Now we are going to draw a lot of the graphs, but we're just not going to do it out longhand and dealing with all these formulas. Just some basic ideas about the standard normal curve there. Cumulative area is close to so all they're saying with this first part, if we're out here somewhere, guess what the area is to the left? 0. So not many scores should fall out in there. 0% of the scores should fall out there. As we go farther that way, it increases. That's sort of obvious. Cumulative area from here down is 0.5 or 50%. So from 0 down should be about 50%, should be about 0.5. Same thing for the area going up there. If we're over here on this side, the cumulative area from here down, we're almost always working down from the left to the, or from the right to the left. So the cumulative area we get out here should be close to 1 whole, should be everything. That table, you have this table, it's on that thing. We're going to use it here in a second. If your number's not on the table, if we're doing something and the number's not on there, just get the closest or make an estimate, something close to it. And again, it looks like this. It's the first and second page of that packet that I handed out to you. The front page, the first page, is the negatives. The back of the first page is the positives. So if we're looking at a z-score and we want to find the area of the z-score of 1.15, so what we're doing, this is our curve, and this is what I want you to be able to draw each time when we do this stuff. You're going to draw your little curve here, put your 1, 2, and 3, and -1, -2, -3 on there. We want a z-score of 1.15, which would be somewhere right about in here. So what we're trying to find is we're trying to find this area. The area of that part of the curve. On the chart, if you get out the chart, you can look at it. It'll be on the second page. We want to go to 1.15. So we go down to 1.1, and we go over to the 0.05 there. That's the third number. That's our area. So we're saying 0.8749, that's the area that's in this part that I just shaded in.
Ebersole?
Yeah.
I heard about
So 0.8749, that's what we said it was. This is what the curve's gonna look like. Gotta be able to draw this curve. We're gonna draw that regardless, whether we use the chart, the calculator, whatever. Gotta be able to draw the curves, shade in the part that you're looking for. The front page is the negatives. So if we want negative 0.24, we go down to negative 0.2, go over to the 4, which is that. I'm drawing this curve, and the curve doesn't have to look spectacular. 0 right there, 1, 2, 3 here, negative 1, negative 2, negative 3 there. We want negative 0.24, which would be somewhere just the left side of 0. And then, again, we're always dealing with, or this chart always deals with, everything to the left. So we're looking at that area. Right away, when I'm on this side of 0, I know that my area should be less than 0.5. So if it's not less than 0.5, then I screwed up and I did something wrong. Well, this area is less than 0.5, so hopefully that's pretty close. So that's what it is. Again, you can use the chart. It's not real difficult to use that chart to find the areas. The thing that makes the chart harder is if you want the area, instead of the area to the left, maybe you want the area between two numbers. So maybe you've got a curve and you want the area that's from here to here. Then the chart is a little more difficult. Or if you want the area to the right, makes the chart a little more difficult. If it's just the area to the right, all you got to do is find the area to the left and then subtract it from 1. But the area in between two numbers is a little tougher. All right, before we write this down, I think how I want to do this. Are you guys going to be smart enough to understand this if I do it all as one thing? Yes, no, maybe?
Maybe.
This is how we use the calculator if we're looking for area to the left. Let's just do it this way. So that's one of the things, area to the left. I'll give you a second, copy that down. If we're looking for the area to the left, that's what you punch into your calculator. When you get to number 4 here, I said punch in negative 10,000. It doesn't matter. You're just looking for some number that's way down to the left, way past anything that we could actually ever want to deal with. So this lower limit here, if you know you're dealing with just regular z-scores, you really don't have to punch in negative 10,000. You could punch in negative 100, negative 1,000, and that's plenty far down there. That's going to include everything to that side of the graph when we're looking at the graph. we're looking at the graph, wherever we're at, we want to punch in the low limit, which is going to be way down here somewhere. The z-score, or the high limit, and that's going to tell us the area that falls on that, from that there down to the left. So if you punch in negative 10,000, that's going to make sure it includes everything. Maybe sort of the bad thing here, that has to be a z-score. So it can't just be the raw score, it's got to be that standard score. Days off killing all the seniors because everybody seems dead. My first class was seemed dead also, and act like they don't want to do anything.
I'm just ready for lunch.
You know what it is?
Yeah, this class makes it feel longer.
I know, right?
It's like everybody else gets to go to lunch at 10:18. Sitting there.
Things you're going to do when you're doing this. Again, and I'm going to expect this every single time. You're going to sketch, so draw a little graph, sketch it, your standard normal curve. Put 0 on there, put your 1, 2, -1, -2, -3 on there, and then put in your score. So if your score is like a -1, put it in there and shade in the part that you're looking for. So again, I'm going to expect that you do that every single time. Especially now on the homework, you know, I don't check the homework real vigorously or anything, so I'm probably not going to look at it, but when it comes test time, I want to see that every single time if we're doing a problem dealing with area or probability on one of these. So you draw the curve, just doesn't have to be anything real special. Find the area, whether you use your calculator, whether you use the chart, whatever, you're going to find the area then, but first thing is you got to draw it. If we're finding the area to the right, so this is a little different. If you're finding the area to the right, if you look on the chart, if I go get my chart and I look on that chart and I look up 1.23, it's going to tell me this area over here. I don't want that area. So if we're using the chart, what we're going to have to do is we're going to have to look up 1.23 and subtract it from 1. So we're going to take 1 minus the number from the chart, and that's going to give us the area that's left out there to the right. So that nothing really hard about that. So on the chart it said that was this yellow area over here is 0.8907. We just subtract that from 1, and that gives us the area out that way. To find the area to the right using your calculator. These are the steps to find the area to the right on your calculator. Notice on this one, you put in the z-score, comma. Since you're finding stuff to the right, put in the z-score first. So you, again, draw your little graph. Got 0 here, 1, 2, 3, -1, -2, -3. If we're trying to find the area from here over this way, then we put in the z-score first. We put in that score that we're looking for first. And then on the other end, we put in like positive 10,000. Or something that, some number that goes out this way far enough to make sure that we include everything. Again, it doesn't actually have to be 10,000. It could be, most of the time, it could probably be 100, 1,000, anything. Just so it's enough to make sure that we're including everything going out that direction. You could probably go as far as only putting in 10, and it would probably still be enough, but doesn't hurt. You're punching 0 to punch a couple extra zeros there. Just to make sure that it includes everything going out that direction. Same idea here. On this one, if we're finding the area in between, so we're looking for this area in here, a little tougher to use the chart. If we're going to use the chart, what we'd have to do is we'd have to find the area from here down, then find the area from here down, and do what with those two? Subtract them. So that's not real hard, it's just takes an extra step. On your calculator, you can do this a little easier. On your calculator, what you can do, you put in the low z-score, put in the high z-score, and it'll do it for you. So what I had started to do, this is the area between. What I'd started to do, instead of having you write down all 3 of these ways to punch it into your calculator, I started to just show you this one. If we're finding stuff and you want your low z-score to go all the way out to the left, then that's when you put in the -10,000. If you want your low z-score or your high z-score to go all the way out to the right, then that's when you put in the positive 10,000. So we probably could have just written this one down. But Trinity wouldn't admit to being intelligent enough to just write one down, so I didn't want to confuse her. Now she's thinking, God, Ebersole, you made me write all that down for no reason. So it's second bar's normal CDF, which is the second thing down on your calculator. You punch in the low number that you want, you punch in the high number that you want. Again, the bad thing with both of these, or with all of these, this only works this way if everything is changed into a z-score. So before you can punch in any numbers, you got to change that raw score into a z-score. A lot of times on the problems that we do, they'll have already changed them to a z-score for you. Yes. No. When do I have Chase? I have him. I have him on break, yeah. That's all right, you're fine.
We'd have to start early.
I don't know anybody's last name, so I have to think who's Chase.
I'll have to see.
So if we're doing this, find the area under the standard normal to the left of -0.99. First thing I'm gonna do is draw my little graph here. That's 0, 1, 2, 3, -1, -2, -3. -0.99 is gonna be somewhere about here. Again, we could either use the chart or we could use the calculator. I don't care which one you use. If we're using the calculator, and I'll let my calculator laying back here. First thing I notice on this, my area here should be less than 0.5 because I'm just finding the stuff down this way. So all I'm gonna do is punch in second, bars, go down 1 to normal CDF, and I want to punch in the low limit, which this time is going to be -10,000 or something like that, and then the high limit, which is this, -0.99. And it tells me, well, that didn't look right, 0.1611. Usually we'll go out about 4 places on these. So go out 4 decimal places, that's about normal finding these areas. Hopefully that ends up being about right. Otherwise I'm gonna look stupid. We want to do to the right. This one, we're 0, 1, 2, 3, -1, -2, -3. We're at 1.06. It's gonna be somewhere about in here. So we're looking for this area. Then you punch all that into your calculator. This time you punch in that first, and then positive 10,000 as your upper limit out here. So we're looking for that area there. The area over this way, they're using the chart. The area over this way is that much. To find the blue area, we just subtract it from 1. But again, the calculator is going to do this for you. You won't have to subtract it from 1. Comes out to about 0.1446. And then if it's the area between, a lot of times when it's between, I made it different here. But a lot of times when it's between, these two numbers will be the same number. We draw the graph, it's something like that. Area there is that much. Area from there down is that much. We just subtract those two, and that's going to leave us with the blue area. Again, on your calculator, you punch in this z-score, and it's going to tell you the area here in the middle. We already did that. I'm not sure why I put that on there twice. This, you got it down there somewhere probably a long time ago. What's X bar stand for again? That's the mean again. S stands for standard deviation of a sample. And just 1, 2, and 3 standard deviations each way. Using the empirical rule again, 34% should fall in these two areas. See if I remember what falls in these two. 13.5%.
2.4.
And about 2.35 in each of those. Anything that falls in here is considered unusual, and you can't see this, but anything that falls out here on either end past 3 standard deviations is considered very unusual. I'm not sure why my slide's down so far. So anything past 2 standard deviations is unusual. Anything past 3 is considered very unusual. That's the assignment. When I worked it yesterday, not a real tough assignment.